Hello, everyone, and welcome back now to the part two of chapter eight. So, in chapter eight, the first part, we spoke a lot about generally what photosynthesis is, the history, how it was discovered, and more importantly, how photosynthesis is divided into two different reactions: the light dependent and the light independent. So, the light dependent is this one over here, where we actually absorb sunlight and we convert that to energy. And of course, we need special molecules to do that. And these are called pigments. Pigments are able to actually absorb energy or photons in the visible light spectrum. So they're able to take it up and then convert that into energy, which then basically kind of funnels or helps creating ATP and NADPH. So that is all the light dependent reaction. And then basically with that ATP and NADPH, what we can do is use them to create actually organic molecules using the Calvin cycle. And this is then the um, light independent reaction where you don't need light because the energy is already supplied as ATP and NADPH. So today we're going to speak a lot about the light dependent reactions and more specifically the photosystems here. So remember, these photosystems are these big structures that are on the thylakoid membranes, and they're the ones that actually are able to convert all the sunlight into energy. So they're sorry about this. My tonsils are a bit swollen, so that's why my voice is a bit weird. So bear with me. So the sunlight is able to be absorbed and converted into energy because of these photosystems. Because these photosystems are structures in the thylakoid membrane that have a lot of pigments. They basically are literally systems of mixture of pigments and proteins all mixed together in this big matrix that create this whole one complex called a photosystem. And they're the ones that are able to do all of the reactions. So let's just talk about the photosystems. So the photosystem is actually has two components. It has one component called the antenna complex, and the second is the reaction center. The antenna complex is actually hundreds of axillary pigment molecules, and majority of these axillary pigment molecules are chlorophyll B. You have also a lot of carotenoids, but they're mostly actually chlorophyll B. A lot of these kind of accessory pigments. And their name is quite self-explanatory because what they do is they gather photons. So they're like an antenna. You know, when you have like a satellite antenna that's gathering basically certain waves. Well, that's what they're doing. They're there trying to funnel or take in all the energy they can absorb. Of course, they can only absorb, so chlorophyll B can only absorb a certain amount, in the spectrum, as we know this, and we spoke about this quite in detail. So they are able to gather them. So they gather them and then they pass them on to the second part, which is the reaction center. This reaction center is a very highly specialized center and where you have one or more chlorophyll A molecules. Because remember, chlorophyll A is the main absorbing molecule that's going to create it into energy. So that's the reaction center. So the first part, the antenna, what it's trying to do is just to funnel, so just to gather all of the photons it can, and then they're going to pass it to the reaction center. And basically, they pass the energy to chlorophyll A, and then chlorophyll A passes then energy as electrons. So the difference between antenna complex and reaction is that here they pass the energy as photons. They really pass the photons on. But the reaction center actually gets the photon and actually will transform it into energy as a form of electron. So that's the main difference. So that's why the accessory pigments are not the ones that are doing, transforming the energy. They're just getting it and they're passing it on, until they reach the reaction center, which is the chlorophyll A. That's the main pigment that does that. It's able to take this energy and it's able to bump its electron off. And that electron that's going to be removed is energy that's going to be fueled to do ATP and NADPH. So let's talk more about the antenna complex. The antenna complex, like it says, that it's also they call it the light harvesting complex. And again, their names are very self-explanatory, guys. That's the nice thing of biology that most of the names tell you their function. They're harvesting light. That's what they do, and they're literally a matrix of proteins and chlorophylls all linked up together that are able to do this. And most of them are accessory pigments that are mixed with proteins together in a matrix that basically are able just to gather or just collect these photons to pass it on to the reaction center. So again, what happens? So let's imagine this is your whole photosystem. So basically, you have a photon, so this energy. So you have these accessory pigments over here. This is basically then your antenna complex. They're just absorbing it. They're absorbing it, and what they're doing is they're passing these energy. Again, please do not confuse. The passing here is not electrons, it's actually energy. They're just passing the photons' energy around until they reach the final part, which is the reaction center. This reaction center is the one that's then able to take in this energy. And this reaction center, as we said, is either one or two or more chlorophyll A molecules. And what they're able to do is they're able to actually take in this energy, and actually it will displace this energy, will give it, they will pass it on to its electron. And once we actually give energy to electron, we can make it move, correct? So when the energy is passed to the electron, it's being moved to an electron acceptor. So something else is going to accept it. So this chlorophyll is going to lose an electron. It's going to pass it on to another electron acceptor. But of course, now this now center is very negative. We need to actually balance this. So we need an electron donor. We need someone to give us electrons, actually, to keep this back to neutral. This electron donor, remember, is this H2A. So in this case, it could be water, so H2O, or it could be actually hydrogen disulfide, H2S. So that's why we actually in oxygenic photosynthesis, we create oxygen because we break water to get the electrons and pass it to this chlorophyll center, this reaction center over here that already lost its electron. So let's kind of show this in a more easier manner. So the light is basically, being taken up by the antenna, and the antenna complex is basically, passing it on to your uh, reaction complex. I'm saying it right? Yes, your reaction center, sorry, which is basically over here, these three little objects. So it's passing it to this chlorophyll A, which is shown in green. So what's going to do is you're actually exciting the electron in chlorophyll A, and that's being passed actually to a electron acceptor. So this could be, again, guys, these electron carriers. So these electron carriers will pick up the electrons, and as we saw, now suddenly this chlorophyll A is a positive charge because it lost an electron. So this is very dangerous. We don't want that. So what's going to happen is that we're going to basically get a donor. So someone that's going to donate an electron, and in this case, it's the H2A, or in oxygenic photosynthesis, it's H2O. So H2O is going to break. It's going to pass the electrons here, and the oxygen that leaves is actually going to basically be released as oxygen gas. That's why we get oxygen in oxygenic photosynthesis. In the case of anoxygenic photosynthesis, this kind of donor is H2S, for example, is so hydrogen disulfide. So it breaks the hydrogens, and they take the electrons from there, and the sulfur is released as basically as a gas. So that's why we get a gas, because we're breaking these electron donors. They're breaking them, getting the electrons to basically kind of neutralize this oxidized chlorophyll right now. So that's what basically happens in this kind of photosystems. So now we're gonna really go into the details of like really what happens in every single step. And if you wanna really put them into steps, you can have them to four. First one is the primary photo event, is where the photon is captured, and this is mostly captured by the antennas. So the antenna complex, which has these pigments, the accessory pigments that are basically harvesting this energy, and they pass it on to the um, this complex, this reaction complex. And this then creates a charge separation where energy is transferred into the reaction center. An excited electron is then transferred to an acceptor molecule. So the charge separation is where basically now the excited electron in the reaction center, so in the chlorophyll A, is being very excited and is being passed to an acceptor molecule, to an electron carrier. And then this electron carrier is actually going to keep moving it to different electron carriers. And actually, they're going to create, actually, in some sort of way, give energy, because when you pass electrons, this is all back to chapter 7. The passing of electrons creates these energy. It gives off energy to these electron carriers. And as we know, some of these electron carriers can be proton pumps. And in this case, it's the same. You're passing the electrons. So the passing of electrons gives this energy to these proton pumps that create this proton gradient, which then basically actually helps us do chemiosmosis. Again, protons are going back through ATP synthase. Is the movement of this. So this is almost exactly the same as what we saw in chapter 7, actually. So what's happening, the new part is the first part and second, where we are absorbing or harvesting these photons, and then we pass it on to our chlorophyll A, which is in the reaction center. And the chlorophyll A, what it's doing is actually getting excited. So the electron is getting super excited and it's being given actually to NADP plus, which is the electron carrier. And then NADP plus then goes later off and starts giving it to other electron carriers. And these electron carriers, some of them are literally proton pumps that create this beautiful proton gradient that is going to fuel chemiosmosis and ATP actually production. So there's two types of actually light-dependent um, photosynthesis. There's cyclic photophosphorylation and non-cyclic. So cyclic, this should basically kind of remind you of the Krebs cycle. Remember? So the Krebs cycle, when we learned in chapter 7, is cyclic, meaning that its products can go back as reagents. So remember in the citric acid cycle, oxaloacetate is basically the last product of it, but oxaloacetate can then go back into the first reaction, so it becomes a circle. So it keeps going back and forth. Well, same thing goes with this photophosphorylation. It becomes cyclic in where now the reagents, sorry, the products, the end, can then start again. So hence why it's cyclic. And this is basically anoxygenic photosynthesis. It's the photosynthesis that does not create actually any oxygen, and you do not create actually any DPH. You only create actually ATP synthesis. So why is it cyclic? Simply because it has one photosystem. This only has one photosystem. So in this photosystem, you have actually your antenna complex, and then you have actually a reaction center, which is shown here. And in this reaction center, we have a chlorophyll A molecule that we call P870. So P870, the number, what it tells you is actually the wavelength that it loves, that it prefers, that absorbs energy. So what it means is that this chlorophyll A in the reaction center, this P870, loves to absorb energy at wavelength 870. That's what the number signifies. Okay? So what happens here in this cyclic light dependent light dependent photosynthesis is that the antenna is going to get the photon, it's going to harvest it, it's going to pass it around until it reaches the reaction center. The reaction center, this P870, is going to absorb at 870 nanometers, the wavelength, and then it's going to basically pass its electron actually into an electron acceptor. This electron acceptor is then passes it on to a BC1 complex. This BC1 complex is another electron carrier, actually. And similar to what we saw in chapter 7, this BC1 complex is also a proton um, pump. So it's going to push and create a proton gradient that's going to funnel into chemiosmosis to create ATP. So when this is done, so it passes the electrons, another to electron acceptor, it passes it back into this reaction center. So basically, this electron acceptor becomes again this oxygen donating. So remember here that we're talking that we need two things. We need an electron acceptor and an electron donor. So our electron acceptor is basically is right here, and then it by itself it also becomes actually the electron donor, because again this reaction center is positive when it loses the electron, so we need to give it back. So that's why it's cyclic, so it goes back and forth. So this can then be used again. Here, one thing that I really want you to really understand here is that it doesn't produce oxygen, and basically this is called used in non-sulfur bacteria. And actually, you produce ATP, but you do not produce NADPH. You do not. The amount of energy that's passed on here is not enough to oxidize, to reduce NADPH. It's not enough. It's only enough to actually funnel ATP, actually. So that's why you need to always remember here the electron acceptors that are taking in, they also become the electron donors. So that's why it's cyclic. It goes in there basically in a wheel. And this you see this a lot in purple non-sulfur bacteria actually. So now let's go into something that is more relevant to basically plants, which basically chloroplasts. If you look at chloroplasts, so these are basically all the plants. They have two photosystems. The first one is called P700, photosystem 1, P700, and photosystem 2, P680. And again, as very similar to what we saw before with the P870, the number again, it's literally tells you the peak of absorption spectrum. So meaning that the chlorophyll A in the reaction center of this photosystem will actually absorb at its highest at 700. This one at 680. So that's the main two differences there. And the beauty of this is that this is not cyclic, so it's non-cyclic. But these guys work together and they work together in synergy. And when you hear synergy, and what it means is that together, when they put them together, actually the addition of them together actually is more than the sum of each one. So I'll give you an example. So imagine here, this is the rate of photosynthesis in the y-axis. In the x, what you're doing is time. So what you're doing here is basically turning on certain lights. So you turn on the far red light on, and when you turn on the far red light on, you turn on this P700. So you see some photosynthesis happening, great. When you turn on basically this normal red light on, you're turning on, sorry, this P680. Some photosynthesis happening, and done. You turn on both of them, it's much, much higher. And the one thing that's really cool is that the amount of photosynthesis here plus the amount of photosynthesis here is still less compared to this because this is synergy. This is basically when they're working even together, they actually create much more than the individual actually. So they're working together. And this was the evidence that came up in 1950s that that chlorophylls actually have two photosystems and they actually absorb at two different light spectrums, one at 700 and one at 680. So we're going to talk a lot about them. They're quite simple, so I wouldn't really be too, afraid of them. So again, very similar. Photosystem 2 here is exactly almost very, very, very similar to the P100, the P870 photosystem. Very, very similar. So what it does, it basically takes in the photon through its antenna complex, so it funnels it, and it passes it into the reaction center, which has a chlorophyll. So the chlorophyll here is going to be actually super reactive and it's going to actually release two electrons because mostly it has actually two um, chlorophyll A molecules. So the two chlorophyll A molecules are going to get excited and they're going to pass two electrons. And these two electrons will then pass into this plastoquinone, which is an electron carrier. So very similar to the quinone we saw actually before. Then this actually then is passed, then it passes its electrons to this B6F complex, which then passes it again to plastocyanine, another electron carrier. This B6F complex is a proton pump. So the passing of electrons supplies it energy to actually, pump out hydrogens. It's going to pump out hydrogens actually, and then this is going to create a proton gradient, which is needed for ATP synthesis. Because now these protons that are out will go back inside through ATP synthase, so chemiosmosis. So when plastocyanin comes in, it's going to pass now. It's actually, so this is plastocyanin. So let's stop here. In photosystem 1, it's going to do the same thing here, and where actually its antenna complex is going to take a photon. It's going to get funnel the energy into the reaction center, and now the reaction center is going to release two electrons. Now remember this reaction center over here. This is now positive because it lost two electrons. The plastocyanin will now become the electron donor, so it's going to pass its electrons that it has to it. So this becomes actually now neutral. The two electrons are then passed to ferredoxin, which is another electron carrier, and again gives it to NADP reductase, and then basically this which then creates NADPH. So that's basically, so this NADP reductase is going to help actually with the reduction. So basically this enzyme is going to actually produce NADPH, so it's going to reduce it. But one thing that we forgot here is that, okay, this reaction center has now become neutral because plastocyanine has given its electrons. But what about this guy now, in photosystem 2? This guy lost two electrons, so we need to make it up because now this is very positive. So water here is going to come, it's going to break, and now you're going to get basically this reaction, and you get two electrons. These two electrons are going to be passed on to your reaction center to neutralize it. And in the consequence here, when you break H2O, you release oxygen. And this oxygen is going to be released as a gas, and this is basically what we breathe. This is because of these reactions that our atmosphere is covered in oxygen. So now let's talk about more details into photosystem 2 and 1, just their structure. So the photosystem 2, it resembles the reaction center of the purple bacteria, actually. So about this photo, about the one we just talked about, this one over here, in this P870. It's very similar, actually. The whole photosystem 2 consists of 10 transmembrane protein subunits. So it's 10 proteins in the membrane, and it has two p160 chlorophyll A molecules. So this is why you get two electrons, because you have two of them, two chlorophyll A molecules there that are getting excited and passing to two electrons. So again, the photosystem 2 has 10 transmembrane protein subunits and basically two p680 chlorophyll A molecules. But the nice thing about these chlorophyll molecules that's very different to the purple bacteria, one, is that it actually has this manganese atoms. So these manganese atoms are literally, they help actually kind of break the water. So what's actually causing this breaking is the manganese atoms in the chlorophyll that here, you don't know, it doesn't exist. That's why it cannot break water. While here in the photosystem 2, it has the manganese atom that's able to break the water. So that's what is able, that gives it actually it's actually its role in breaking the water. Then you have the B6F complex, so it's this guy over here, and then there's a proton pump that's also in cyclode membrane. So this is the one that basically, when it gets its electrons, it gets it from plastoquinone and it passes it to plastocyanide. And this passing gives energy, and this is what's funneling because this is a proton pump. It's creating a proton gradient, and it's actually creating the perfect, you know, um, circumstances for chemiosmosis, which is the beauty of it. So now let's go into photosystem 1. It's actually quite bigger because it has 12 to 14 subunits, and it actually has two bound P700 chlorophyll A molecules. And again, this explains why you have two electrons being removed here. So here, in this sense, the P870, you have one electron because you only have one um, chlorophyll A molecule, this P870 chlorophyll A molecule, just one of them. While here, in both these photosystems, in photosystem 1 and 2, in the reaction center, you have two chlorophyll A molecules. That's why they're releasing two electrons. It's quite, straightforward. And they basically also, they're a bit bigger than photosystem 2 because they have 12 to 14 subunits of basically, transmembrane proteins. And as I said, the good thing about the photosystem 1, it accepts electrons from the photocyanide into the hole created by the exit line ends of the electron. So meaning that what it's saying is that so now the hole that you created here where the electrons left is being replaced here with plastocyanide. So that's the thing, the beautiful thing of it. This is why it's not cyclic, because this is not going back into here. It's going into here. So you see, this is not a cycle. While this over here is the whole cycle. So it literally is like a circle. Well, here it's not. This is not a circle. And here, what it does, it passes the electrons to NAD plus to form NADPH. So this is where you're creating NADPH, and so the photosystem 1 is actually needed for NADPH production, while photosystem 2 is needed for ATP. So as you see here, the B6, because it's this B6F complex is in the photosystem 2, and that's the one that's going to create actually the proton gradient, which is going to create ATP. Well, the first photosystem 1, what it does, it creates NADPH, which is then needed later. So here, the products here, which is ATP, and the products here are needed for the Calvin cycle later on. So again, this is just a more simplified kind of figure. So I'm going to go over this because it's quite cool. So what happens here is that a photon is basically then taken absorbed by the antenna complex, as you can see here. The antenna complex is passing it on and on, actually, in a way that is actually exciting your reaction centers. So the two chlorophylls here, that there are P680, they're being very excited, and they're passing it to plastoquinone. Plastoquinone then is passing it to this B6F complex, and this B6F complex right here is a proton pump. So it's going to release actually the protons into the cyclode membrane basically. So it's passing it to the cyclode membrane. So the stroma, so it's taking actually the hydrogens from the stroma into the thyroid membrane. inside the cycloid space, sorry, into the cycloid space. Then these are then going back up into same through the ATP synthase through chemiosmosis. Because basically here there's much more hydrogens compared to outside, so you're creating a perfect gradient for them to pass through. So again, very similar to chapter 7. Then plastocyanine is then giving its photons basically into the photosystem 1. But it's this photosystem 1 was what happened before that is that it also got a photon. It made its reaction center excited, so it lost 2 electrons. So plastocyanin is basically neutralizing now the reaction center, the one that already lost its electrons. But this electrons that passed now from photosystem 1 is going to ferredoxin, and that's then basically going and passing it into NAD, NADP plus to create NADPH with the help of NADP reductase. So that's what's exactly happening here in this part. So this is a very beautiful, actually, summary of it. So as we said, what you're doing right now here is that you're creating actually NADPH and ATP from this non-cyclic photophosphorylation. That's going to help you actually go into the carbon cycle. So remember, non-cyclic phosphorylation creates this. Cyclic only creates ATP. Please remember that. So in part 3, we're going to talk about more carbon fixation and the carbon cycle.